You guys are proceeding well on the next thing that is due, which is term paper. I saw some questions and clarified. If you have any other things, do talk to me in the office hours and get those clarified. We are going to start new module today, which I have posted, which is on the data dependence analysis and loop transformations, which is our next topic, which is really a very interesting topic for multiple purposes, modern compiler topic, which is getting used. And so we are going to talk about that. And then after that, we'll do some machine-specific optimizations. And that will conclude the semester. A couple of papers we'll see which are on that topic. And then time permitting, we can do as a part of the machine-specific optimizations, a brief introduction or revisit a little bit of register allocation. I think it's already done. I'm assuming as a part of your main compiler class, undergraduate, because it's an essential part of that. We do it in 40-40, but we'll revisit just in case some have not done it. So before I start the new topic, are there any questions, or do we need to revisit anything in the SSA-based optimizations in general, on any of the SSA topics, or in particular on the GVN, global value numbering, which is actually the key optimization which is implemented in LLVM and many other modern compilers. It is the pinnacle of all the optimizations and subsumes many other optimizations. So the GVN pass is the most important one. And as I was mentioning last time, it's basically an extension of making sure that the values are equivalent to each other in the broader scope of the complete CFG, extending the scope of value numbering from extended basic block to the global scope of within a procedure. And the way it was done was we used a value graph to implement the congruence relation, which is about the values being equivalent, and transitively carried that out using the operations on those values, they being congruent and their respective operands being congruent. And then the operations included not only our arithmetic operations and other comparisons and any other operation, but also included the SSA operation, which is a very important one, which is the phi functions. And again, note that the phi functions were equivalent only for a given basic block. In other words, the two different basic blocks are two different phi functions. And so they will be not equivalent because obviously they represent values flowing into different blocks and in different ways also. Again, the phi functions only within a block are equivalent. And on one edge, again, the operands should be congruent to each other. And on the other edge, also the operand should be congruent. And that's how the transitivity is incorporated in terms of the phi functions for value numbering. And so therefore, we are able to extend the value numbering in a global sense. And then the other part of it was relatively simple, two fine points here. One is it's an optimistic formulation, again, like SCCP and all that. And that guarantees the convergence of the solution in an optimistic way. Otherwise, we would determine the two values may not be congruent to each other. If we start in a pessimistic way, we will arrive at a different fixed point. And then the second part of this, so make note of this, that we assume that all plus operators, for example, are equivalent to each other. And then if we can prove that they would be different, we would separate them out. So that's the optimistic formulation. To begin with, we assume them to be equivalent unless proven otherwise. And then the second part of it is that once we prove a congruence, we have to make sure that in order for one value to really replace the other, we must have both simultaneously present at a given program point. In other words, that program point must be dominated by the respective values, which is actually the SSA's way of saying that both are prevalent there. And so you could change one to the other being prevalent in a given point. So that's the other part. Make sure you note that as well. And so go through the examples on the slide if you haven't done it already in the book. And there is a very nice implementation of GVN in LLVM. I would kind of play with that. Of course, I know that you are we have a lot of stuff going on, so I'm not giving any exercise related to it. But I will leave it to you to play with it and use the interfaces and see the effect of GVN on some test cases and some example codes and so on, and see the effectiveness. There will be some test examples there, or you can run it on your own benchmarks and see how GVN really captures multiple things, which is CSE, of course, common sub-expression elimination. It also captures the non-lexical equivalent, as we have seen, and any other things such as two copies being equivalent. It is also a special case of a GVN. Constant propagation, that's also subsumed. So you can see that many optimizations which are really redundancy oriented or propagation oriented taken care by the GVN. So it's a very nice pass, and try to see its output and play with it if you can in the LLVM. So, and that's the last, of course, SSA's optimization pass that we are, optimization that we have seen. There used to be a GVN PRE, which is PRE version of global value numbering, which used to be present in LLVM, but I believe that has been removed in the recent releases. However, you will find some older releases, and moreover, if you maybe I will put a paper just for your own reading, not really for any exam purposes or for any homeworks or anything, on GVN PRE, just to complete our understanding that GVN can also be extended for partial redundancy removal. And the lexical and non-lexical bases again are tackled there. Of course, GVN is very useful in the middle end, and PRE, as I had been mentioning, is more useful in the register allocated versions because of the namespace issues. But there are, of course, some cases of PRE which are present even in the register allocated sense, which may not be lexically identical, and those are tackled again through GVN PRE. So take a look at that paper which talks about all this. If you have any questions on GVN or any other SSA, please don't keep it to yourself. That is a very important part of modern compiler infrastructures and in general. And I'll be happy to answer anything during office hours. Please do come if you have any such questions. All right, so with that, I think I will move on to the next topic, and we will get going with the stuff here. And this is a topic which is very interesting, very useful for modern compilers in two sense, in two different ways. One is, of course, we have been looking at the optimization so far terms of redundancies and constants and better code generation, and they have tremendous, of course, implication in terms of performance. But as you know, the performance also stems from the loops and optimizing the loops. And in the modern compilers, of course, you can see that the performance bottleneck is shifted to memory and its access. And of course, it's tackled in two different ways. One is by register allocation schemes, which prove to be very, very important in modern compilers to solve the memory bottleneck by trying to keep the values as much as in registers. But obviously, we cannot keep all the values in registers. So the second way to do this particular optimization, which is to avoid the memory bottleneck, is to maintain temporal or spatial locality. That is by making sure that the consecutive accesses lie on a cache line, which is a spatial locality, or different cache lines do not get evicted during the course of execution of a loop, which is a temporal locality. So you must have heard these terms in your architecture classes. So what is a spatial locality? When you bring in a cache line into from the main memory into a cache, obviously you are bringing more data than you need during that particular cache line access. Now, if you reorganize your accesses or your data in such a way that they fall on the same cache line which you have fetched, you will incur a locality, you will find the data in the cache, and you will have a hit on all those accesses, and therefore you will not pay the miss penalty of going to the memory and blocking and whatever on that access. So this is called a spatial locality, different accesses, consecutive accesses falling on the same cache line and arranging them, or the data layout or the underlying accesses in that manner is called as spatial locality. The other implication is, of course, as I mentioned, if you're accessing a data and reusing it after a long number of iterations, that particular cache line which has that data should not be evicted between the two accesses. And that is special, that is temporal locality, because it occurs at two different time icons. So preserving that also and making sure that the reuse is found within the cache is another important way of organizing the loop. So we can either organize the data or we can organize the accesses. And obviously, if you keep reorganizing and organizing the data, you'll have to move it around in the memory. Sometimes you can't even do that because of the conventions that are adopted in certain languages. That, for example, Fortran says that your metrics should be laid out in a row major manner because many libraries and other things expect that layout. So that's a linkage convention which you cannot violate. So you don't have much flexibility in terms of doing some of the changes to the data layout. Sometimes you can do that. It could be also expensive to change the data layout. So you try to reorganize your accesses to match the layout. And that's basically what we call as loop transformation. So this is one reason for doing this analysis, to be able to carry out a loop transformation. And we want to understand what are the constraints which must be satisfied in terms of changing the access patterns in the loop. And that's why data dependence analysis. The other goal for which this particular analysis is really used is parallelization. So you have a loop and you want to split up the iterations and execute them in parallel, which is what is very important on modern multi-core processors. And whether you can do it or not, that is decided by the access patterns and the data dependencies in the loop. And to check the legality of doing parallelization, we do this data dependence analysis. As you can imagine, most of this analysis is pertinent to array accesses and array reference patterns that occur inside the loopness, and that is the premier focus of data dependence analysis. So let us understand the basic concepts here of dependence analysis. Let's then take it to some breakdown of the analysis in terms of array references, and then we will see some loop transformations after that. So let us introduce some of these concepts here in this particular module. We want to understand, we already talked about control dependence and all in terms of the dead code elimination, all these optimizations, but we are here very much interested in finding out what exactly is a data dependence. It is a different concept than data flow, as you will see. And then we will get into some classification of this data dependencies for scalars. We'll understand those. Scalars means no arrays. So true, anti, and output dependencies. And then we'll worry about how these dependencies play out inside the loops and for parallelizations. We'll worry about certain concepts here, which is dependence distance, loop carry dependence, etc., etc. And then we'll worry about how to use this information in terms of ordering, reordering loops. How does it help? And then finally, we'll worry about the dependence testing, which is very, very important to precisely find this information and what are the limitations on the precision and so on. So what exactly is the difference between the data dependence and the control dependence is you can see that in the top level example, we have these values of pi and r, and they are being used in the area calculations. So you can see that it's all executing these different statements. And there is an order here which is implicit, which is lexical order in which this executes. But what is the important implication here is that you can see that as far as the statement S3 is concerned, it needs data from both S1 and S2. And therefore, it cannot execute before them. So our order of execution must be S3 must follow S1 or S2. Because if it executes before, let's say S2, then it will have an old value of R there sitting, not 5.0, and that will of course be wrong in terms of doing the calculations. So there is a certain data flow which is involved here for this particular, which forces this order. Now, if you look at S1 and S2, however, they can execute in any order. So we can have S1 followed by S2, or we can have S2 followed by S1. So we have some flexibility in arranging S1 and S2 in terms of their execution, but we have no flexibility in terms of S3. It must follow the S1 and S2 both. As against that, control dependence, of course, is a very different artifact. It just enables whether a particular thing executes or not. So we won't get into that. In terms of formal definition of data dependence, therefore, we define it in this way, that there is a data dependence from a statement S1 to statement S2. Or in short, we say that S2 is data dependent on S1 for some reason, is that S1 and S2 access the same memory location, and at least one of them stores into it. That means either one of them is a write, at least one of them should be a write. And depending on what the order of reads and write, there are different types of data dependencies, which we'll see. But the other condition is there should be a feasible execution path from S1 to S2 that allows the execution of S2 to get some data or overwrite some data from S1 and things like that. So these are the two conditions. The second condition is pretty much taken for sort of granted, in the sense if both are inside the loopness, and unless there is some either infeasible path, which is of course very difficult to prove at compile time. So we assume that it's going to be there. So we cannot really rule on paths at compile time, as you know. So we assume in many cases they are there, unless we can prove otherwise, that there is no possibility of a path, in which case we will not consider them for a data dependence. But other than that, we will assume. So we might, in some sense, be conservative here. Again, the conservative approximation plays out here like this. Then let's say there was no feasible path, but we assume there is a path from S1 to S2, and because of which we also analyzed them and we found some dependence from them. Now, because of this reason, we are not able to change the structure of the program because of this dependence. For example, in this previous case, there was a dependence of S3 on S1 and S2, and so we could not move S3 anywhere earlier than this. And so therefore, we were concerned. But of course, this is a feasible execution path, because we know all three will execute one after the other. But assume that there was some complex control flow between S1, S2 towards S3. And that control flow, we had to assume that is feasible path, because of which now we detected this dependence, as we see here in this definition, and because of which we are not able to rearrange it, and because of which we lost the opportunity to optimize. So this is again the infeasible path, same problem. Raising its ugly head and trying to prevent an optimization because of the way we are conservatively able to analyze it by thinking that it is prevalent or it is feasible paths. But in addition to that, we have another one here. Maybe there is sometimes feasible path, but there is no dependence. Like in this particular case, there is no dependence between S and S2. S1 and S2, and therefore we are able to interchange it. And that gives us some opportunity to do certain optimizations, even in the conservative sense of this assumption. So which will, of course, leverage, and we will use it to do an optimization in terms of rearranging the program, transforming it, and that changes the orders of accesses. You can see that S1 followed by S2 means we are accessing pi followed by R, whereas in the reverse case, it will be R followed by pi. Okay, so with this, now let's get into, you might be wondering, really speaking, we need a value from one statement and we need that to be used in the next statement. So we can imagine that kind of dependence, but why then are these all other kinds of possibilities which exist? So let us look at the most familiar one first. Here on the leftmost side, we have S2 dependent on S1. So what we call that as dependence is there is a write going on in X1 first, X first, and there is a read of X going in the second statement, S2. And so you can see that if this is the original program order which we have, S1 followed by S2, a value is produced, which is X in S1, and value is used in S2, the X memory location. And we cannot interchange it, because if we do, we will be using an old value of X in S2. We cannot do it. We need a new value of X, which is generated in S1. So this relative order must be preserved. And the reason it must be preserved is because S2 must use a new value of X as per the program semantics, which is generated over there. And so this dependence is called as true dependence or also flow dependence. We'll see in a minute why it is called as true dependence. It's data flow dependence, I think, is the more accurate name for it, but it is also called as true dependence because it cannot be removed no matter what by doing any kind of changes or anything to the program. So a dependence which is carrying the flow of values going in that direction from a write to followed by a read, that is called as a true or flow dependence. Now go to the middle box here in this, and you can see that there's a totally different thing that is going on. What is going on is S1 is reading a old value of X, and S2 is writing into that X over there. And you can imagine that the first S1 is doing a read, the second one is doing a write. But there is still the same order needs to be preserved, because if you interchange it again, then S1 will not use old value of X, which is the intention here. In the original program, it is using old value of X, and if you interchange S1 and S2, first there will be write followed by read, so it will be forced to use the new value generated by S2, and that will be wrong. So we must again maintain here the same order, that the read must be first and there followed by the write. Now that is, this kind of dependence is called as anti-dependence. S2 is anti-dependent on S1, that is what is shown here. And again, this prevents any changes to the order of the program. Now you may say here that, oh, why don't we use SSA and all that? Remember that these classification of dependencies is at the level of access. In other words, we are looking at X sitting inside a memory location. It's not a symbolic reference that we are talking about. And we use SSA and other things for analysis purposes, but as you know, later on, we cannot have 10 different, if there are 10 different definitions of X, we cannot have 10 different values sitting in the memory. It will be extremely inefficient, and it will gloat the memory like anything. Many cases, these X's are not even scalars. They're huge arrays of, let's say, thousands of elements or even millions sometimes. And if you had to create multiple copies, which are different in terms of their names for their implementation, that is actually giving them memory, the program will explode in terms of its data space requirement. So that is just not possible. So we must therefore not assume that this is in the SSA form, because again, this is not about analysis side of it. This is mainly about we are ready to actually generate code, give out memory, bring in the data, refresh the data, and generate the instructions, schedule them, and so on. So that is where we are talking about this type of a problem. And so again, it is not a SSA, it is a regular form in which we are going to not give memory for different copies of the same, different definitions of the same variable. So that's the assumption here. Now the third type of dependence, which is very similar because of, again, being two writes going to the same memory location, is a write in X of X in S1 and write in terms of X to S2. And this is called as the output or write after write dependence. And again, we cannot change the order of this particular generating these writes, because between these writes there could be some uses of X, and they will get disturbed again by this particular writes violated. And even if they aren't, many times there is some exceptional processing code which is implicit or the exceptions processing support in a given particular processor, in which case the first X will generate a different kind of exception. If we move the order, we change the order, there will be huge implications of that. So again, whenever we see first right and there is no use of the the second generation of X, which is based on the output to the right being written to the same X, we cannot change their order. So the anti and output dependencies, to some extent, we could remove them by giving them different memory locations. But again, in practice, we cannot remove them on a large scale because they will lead to a lot of memory explosion. And that's why the one dependence which is we just cannot remove no matter what we do is called as true dependence, or the first dependence, which is flow dependence. Now, the dependencies are very critical for the program order, as you must have realized this, and they are even more important in terms of loops and their parallelization. So typically what we do in terms of parallelizing a loop, as you know, a loop executes for, let's say, thousands of iterations. And one way to parallelize it would be to take different iterations and give it to different processors and execute them in parallel, so that we don't hold back a particular room for a particular iteration and continue to speed up the loop. So let's say there are 1,000 iterations of a loop and we have 20 processors. So if we are able to split them up, each one of them will get 50 iterations, and because of which we'll have a 20 times faster execution. If all of them, the processors can handle them in parallel, each processor will execute 50 iterations as against 1,001, and that's where we'll get a speed of a factor of 20. And that's a simple way of parallelization. Many loops exhibit this type of parallelism. But whether or not we can do this, all these iterations in parallel with each other, is decided by what is called as a Bernstein's condition, which is based on the dependencies. So let's consider I1 and I2 as two iterations which we want to execute in parallel. If we need to do that, if we have to execute I1 and I2 into a parallel, in parallel manner, then we should satisfy these conditions. So I1 should not write into a location that is read by an iteration in I2, because if it does, then we will be violating the flow dependence, because original intent will be that I1 occurs, let's say, first, writes into that location, and then that location is read by I2, and so the write followed by read condition is there in the original code, but it is now violated because we are going to execute these two, I1 and I2, in parallel. So the original guarantee that we had a value into generated by I1 first, and then it is consumed by I2, that is gone. And so the true dependence will be violated, assuming I1 occurs before I2. And in a symmetric way, one can argue the other way also, and that would be anti-dependence, which is getting violated. Now the second condition is iteration I2 does not write into a location that is read by iteration. So again, let's assume that I1 occurs before I2. And so originally what we were doing in the loop was that we were reading a particular value out of an iteration, out of a particular location, and then we're writing into that particular value. So read was occurring before in I1 and write was occurring in I2. And if we try and parallelize this, then there will be a problem again, because the orders in which the read-write occurs will get messed up. We will not be able to preserve this when I1 and I2 execute in parallel. And so the condition here is we don't have this particular read-writes occurring in the original code. The third one is very similar, which is preserves the output dependencies. If I1 and I2 write into a location which is supposed to be rewritten by the other guy, then the relative orders of writes will be violated. And as for the previous condition, what I mentioned, output dependence will get violated. So in order that we need to have parallelization, therefore, the sets of memory locations which are written by the different iterations should be disjointed. That is the premier condition for parallelization. So if you collect L values in iteration I1, if you collect L values in iteration I2, if you collect L values in iteration I3, and analyze them and intersect them with each other pairwise, we should find that those L values must be distinct, disjointed for different iterations. And if that is not the case, if one of them overlaps with the other, then there is a problem in terms of a read-write pair, and the order doesn't matter because it could be an anti-dependence or it could be flow dependence. So if there is an overlap between the read-write sets of different iterations, that's a problem. And the other problem is that there is no disjointedness between the write sets of two different iterations. So again, they'll get messed up. So here is a good example of simple cases of where the parallelization fails of different iterations using these concepts. So look at the left-hand side loop here. AI is equal to AI plus BI. And you can see here that it's, as far as each iteration is concerned, it has its own set of writes which it carries out and the sets of reads which it carried out. And across the iterations, you can see that the reads they carry out and the writes they carry out are disjointed. If you take, for example, writes of iteration 1, it will be A of 1. If you take reads of iteration number 5, for example, there will be A of 5 and B of 5. So you can see that these references, A of 1 and A of 5, they are different. Obviously, A and B are not alias with respect to each other, and obviously the B's will never have any problem as such. But the A's will be problematic if one of them were writing into that location, second were reading. And so in this case, they are not, and therefore there's no read-write conflict between two different iterations, or write-write conflict, which is not possible here also. Because A1 and A5, the iterations which the array references are different, and so there's no write conflict as well. So there's no read-write conflict, there's no write-write conflict, which could be potentially there because of A, and it's not there, and therefore the parallelization is just fine. We could take this loop up to n and put it on as many processors as we have, execute in parallel, and we'll get a beautiful speed up here because of that. However, if you go for the right-hand side examples, they're all problematic. One by one, we can quickly take a look at it. A of I plus 1 and A of I, if you consider those two, one is the L value, A of I plus 1 is the L value, which is the write, and A of I, which is read. And if you consider two different iterations, you can see that they will have an overlap. So for example, iteration 5 will generate a of 6 as a L value, and iteration 6 will generate a of 6 as a R value, read value. And since it is talking about the same value, a of 6, iteration 5 and 6 cannot go in parallel. Because of this, one produces the write, and in the next iteration, we consume the value. So this is a case of flow dependence here. In the original loop, you generate a of 6 in iteration 5 as a new value. And in the iteration 6, which is the next iteration, you use that newly generated value on the right-hand side, and that has to be preserved, so 5 and 6 cannot go in parallel. Similarly, if you consider 6 and 7, they cannot be in parallel just because of exact same reason. A6 will be producing the value a of 6 in the will be producing the value a of 7, I'm sorry, in the 6th iteration, and a of 7 will be consuming it, and there will be dependence between them. So each pair of consecutive iterations has dependence here, and you say because of this reason, this whole loop will execute sequentially. In the next one, you can see that there is exactly reverse case, a of I minus 1 and a of I. Let's consider iteration 5, and that will be reading a of 5. And you can see that the next iteration, a of 6, will be writing a of 5. So iteration 5 and 6, they will have a dependence because a of 5 is being read in the 5th iteration, and a of 5 is being written in the next iteration. So this 6th iteration. So there is an anti-dependence there, and that leads to the problem. Now, the last example is you can see that there is something else going on here. Again, consider two different iterations there. I equal to 5 and I equal to 6. You can see the problem here is the scalar s. Both of the statements or both of the iterations are doing reads and then writes, and they share the same variable s. So if you put 5 and 6 in parallel, you can see there will be a huge issue here, because one of them will be trying to write and second will be trying to read. And again, any order of execution here will be possible because they are executing in parallel, these iterations, and there will be semantic violation there. In this particular case, what is the assumption here? The assumption is that first the read takes place in a given iteration, then we write it in that iteration, and then we move on to the read in the next iteration, and then write iteration and so on in the left iteration and so on. So this order is implicit in the execution, so we'll have to execute this loop also in sequential manner. So you can see that such read-write conflicts mainly, or write-write conflicts, is the reason for lack of parallelization. And so the question is, how do we detect, how do we make sure that maybe the code on the left-hand side, which is AI, is just fine, but the one which has I plus 1 and A of I, on those two examples, or using a scalar s, is problematic for non-parallelization. So that brings us to the concept of what we call as automatic parallelization, or optimizing compilers must analyze the data dependencies for loop parallelization and vectorization to be able to say that, hey, you know, these operations or these particular executions are fine in terms of being executed in parallel, and these are not. And this general concept of what can execute in parallel, I mean, you can imagine that it is really not about where it executes. It could be in the vector unit. Both of these things can execute in parallel, or they could be on two different cores, and they should not still execute in parallel because they violate this relative order, which is important. Or they could be in distributed machines far across the globe. They still cannot execute it in parallel because they don't have any particular order associated with it. And so the detection of parallelism is a separate issue than where the parallelism is exploited. We could do it inside a vector unit, inside a machine, like a very powerful laptop or desktop will have a good processor which can just analyze the instructions in terms of the vectors. Or we could have multi-core machines, which is the case nowadays with 8 cores being very common, and we could put them on 2 different cores. Or if we have an access to a cluster machine, we could put them on 2 different nodes, or even go access to a supercomputer with thousands of processors and cores and so on. We could schedule them and execute them in parallel. So where we do it is a totally different issue, as I said, but whether or not we can do it, whether we can execute them in parallel, it's a matter of the dependencies, and that must be done by the compiler. So it is really a compiler problem. So let us look at different kinds of quickly parallelisms here, which is not really the aim of this class though, but just to quickly introduce you to some things. And there is a 6245 different class offered occasionally by Professor Sarkar, which deals with some of this more parallel stuff. So here is a typical organization. The processors inside a mesh, and they could communicate with each other. And one possibility of a machine is a SIMD model, which is simpler than MIMD model, in which all the processors operate in lockstep. And data parallel machine and GPUs is an example of that. Vector machines used to be the predecessors of these, and they exhibit these data parallelism. But again, the idea there is these deal with different pieces of data which are coming probably from different iterations, and there should not be any dependencies of read-write between them. There could be dependencies like read-read. Both of them reading the data, but if one of them is writing, then that's a problem. Because as per the original semantic, there will be, one of them will be before the other in the sequential sense, and that will create a big problem in terms of implementing these dependencies. So we don't parallelize in such cases. So again, there are all these kinds of parallel machines, multiprocessors which share certain memory, multi-computers which are like distributed. They have a distributed memory, or they do message passing between different nodes, or something in between. We have sharing of the memory between a certain number of processors, and then that memory is coupled with some other memory, and they share the cluster shares a memory and then goes across the network in multiprocessing message passing manner. So what are these implications? These parallelisms have different characteristics. One of the big things that is there, as once you detect that something can be done in parallel, the question is, what is the most efficient way of carrying this operation in parallel? So you could vectorize it, put it inside same processor, or you could go across. but then you have more latency, but then you have more granularity also. You can do it not just for 8 values which sit inside a vector, but a much larger number of values. And then it doesn't scale. The shared memory doesn't scale beyond a point, maybe 100 processors or so, or beyond that. If you want many more to do it in parallel, then you want to go on the multi-computers, which are the nodes and which do message passing and so on. So again, as I said, how to do the best parallelization is a different issue. But our goal here is whether one can do parallelization and analyze these parallelizability of these operations. And so many times the analysis helps to undertake the transformation of the loop. Once we find that something can be done in parallel, we are able to do a transformation of that so that the transform loop can execute in a very good parallel manner. So here is an example of, and that needs different kinds of analyses. And that's what I would like to point out here, and then perhaps start gearing towards the kind of analysis and how do we start getting ready for that in the next few slides. So you can see that the top level box here, we have pretty nice, what do I call it, nice nested loop. And this should remind you of matrix multiplication code, which shouldn't be a surprise that we are multiplying A and B matrices and accumulating the result, the matrix multiplied result in C. Now there are several possibilities of parallelizing this particular code, and still now of course, depending on the different architectures and the kinds of matrices that we have, and many other factors, even the sizes of the matrices and so on, there are many strategies which are possible for parallelizing this. One of the simplest way to parallelize this would be that, hey, can we take the outermost loop here, which is going from 1 to n, and we can spread out all these iterations of these loop in parallel. That is, each of the rows that we are generating here can be generated in parallel. Is there any data dependence here that exists out of these particular thing which prevents this type of parallelization? So you can see here that as far as if you analyze these statements which are within the body of the loop, and look at there again, read, write sets and so on. So there is an initialization step for C of ji equal to, which is a write. And then as far as the I loop is concerned, for a specific value of I, for different values of j, we will be initializing this whole C, which will be a row of that particular matrix. And then we'll be accumulating into, again, that row in the inner K loop. And at every point, given a fixed I, we will be accumulating in that particular row in terms of j and k, which is going into different pieces of the different parts of A and B matrix. So if you look at the read-write sets again, first of all, A and B are totally different, and the only possibility of a dependence could be between the C's. And you can see that as far as the C references are concerned, between two different I iterations, there is no dependence. Within an I iteration, yes, there is a dependence, because first we read, let's say, C of j of I, and then we write into that same location in the same iteration there. So there is a dependence there, but not across different values of I. So for example, if we take I equal to 5, if we take I equal to 10, we can say that we can easily see they refer to totally different values in the C metric space there, and therefore there is no dependence. One indexes a different column of C, so to say, and the other one again indexes a different column of C, so to say. So they are working on totally different columns as far as C is concerned, and therefore there is no dependence there in the I space. So since there is no dependence, we can take all these iterations and parallelize them, boom, in the top level I loop, and we can get a nicely parallel loop outside, and we can execute each different versions of different iterations in a different processor. This we call as the coarse parallelization. Here you can see that each processor will carry out a different iteration of the outer loop, and it will have a good bit of work associated with it, and it will run that in parallel with the other. So if we have, for example, 1000 by 1000 metrics, whatever we are trying to multiply, which is fairly common, in fact small these days given the ML and other workloads, and if we have 100 processors, we'll get a nice speed up of 5x here, because all the processors will execute 5 iterations, sorry, we'll get a nice speed up of 100x because all the processors will operate in parallel and do the work. Each one of them will get 5 iterations. Now imagine a different type of a system which we don't have these 100 processors, but maybe we have one really powerful laptop which has a very high amount of vectorization engine built into it. These days the vectorizers can go up to 256 elements on AMD kind of cores and so on. So let's say we have a machine in which we have a good amount of vectorization going on. So what can we do with that kind of machine? How can we speed up this code on that machine? We can vectorize it. And you can see here that the loop now we need to make sure that the chunks of C loop which we execute in J loop nest and in K loop nest in terms of the consecutive accesses, we can nicely chunk them up and vectorize them. So simplest way, you can take a look at C of Ji here. So in that do loop, we were going sequentially from 1 to n and putting zeros there. Now what we are doing is we take this 1 to n execution there of J loop, but we break it down into chunks of 64 at a time. So we take it from J to J plus 63, and in parallel we execute all of them in a vector unit. Here it assumes that the vector size is 64, and in parallel we simply initialize them to 0. Then we take the next chunk and again do the same thing, and so that way we can get a nice speed up of here which is 64 times because we are, instead of loading one by one, we are loading zeros 64 at a time. Now the same vectorization is carried forward not only for this initialization, but you can see that In fact, any processing that we are able to do on C, same vectorization we are doing, taking the 63 or 64 things at a time, taking this the values which are generated in the body of K loop, doing the addition of or multiplication of 64 parts of J, multiplying this by this particular K in A, which is 64 elements, multiplying by B of K of I, which is like a scalar multiplication to those. So vector is multiplied by scalar, that's one thing. And then there's another vector there, C of J of 64, which is being added. And so through a combination of vector units, we can again nicely do this. And this we want to ensure that there is no dependence in the J dimension here between different accesses with regard to J, which happens to be the case. So there's no dependence on the J side also. You can see that in the top level, all J elements of that loop going from 1 to n initialization, they refer to all different J's. That is one thing. And the second thing is in this K loop down there, we are also referring to totally different J's here. There is no dependence here in terms of the J dimension. So we have this degree of freedom here, which we can vectorize using the J loops, or we can parallelize using the outer loop. We may have different possibilities. We may have possibility of, in fact, vectorizing K loop also, because there's no, you can see that there's no dependence per se on the K side there. In terms of generating these, we'll have to do a different restructuring, of course. What we'll have to do is we'll have to take the first 64, we'll have to rewrite this loop in a different way. JK and BKI will take these vectors in the K dimension and multiply them, keep the partial sums ready, and then we'll accumulate them. So it's slightly more complicated there. We'll have to store intermediate values as the vector products and then accumulate them. But that's a different thing. So again, how we restructure, where we put them, whether we do vectorization, whether we do parallelization, those are different questions which we'll still have to answer. But the question is, in a given direction, can we do it legally? And that's the question which the data dependence analysis answer. So how does it do it? And let's kind of get started on that particular front. What we do here is first transformation we will do is we will try to come up with a normalized iteration space, and that is to facilitate the analysis and more importantly to facilitate the transformation which immediately follows this. So for example, if you have this loop going from 100 to 20 and down by 10, and these are some kind of loops people write in Fortran and all these things, languages, and you can see that it has a stride, which is 10, and it has upper bound and a lower bound and so on. And then it has references with this I dimension inside the loop body. What we'll do is we will normalize the space. What is a normalized space? Normalized space always starts with 1 as the lower bound, and it ends at a certain upper bound. And it has always a unit stride. And that is the definition of a normalized space. Again, it starts with the lower bound as 1, upper bound as whatever it will get determined. And it also has a stride. That means at every point the loop increments by 1. And that's the first step, what is called as the loop normalization pass. That will take the original loop, do these changes, and make the new loop as a normalized one. And in that process, you can see that it changes the index variable of the loop, or iteration variable of the loop, and the transformation is very straightforward. The new index variable is generated as follows. It's shown here by substituting it with I, small I being equal to 110 minus I divided by 10. And the key idea here is to be able to get the lower bound equated to 1, and the stride being reduced from 10 to 1. And the general formula is shown here. I is equal to I minus L plus S divided by stride. And obviously the in this particular case, you can see that if we apply this particular transformation, then the value changes in this particular way. And the new loop that we get is do I is equal to 1 to 9, and the I gets substituted there by an expression which is coming out of that. And the original value of I will be changed into I believe 110 minus 10 times small I. That's what the new value of the original value of I will be substituted. And so if we do this and change capital I to small I using this transformation, this is what we'll get everywhere. And you can see that now this loop is set up for in terms of small I going from 1 to 9, and it pretty much mimics whatever that loop was doing. You can see that if that loop was going from I is equal to 100, you can verify that in this case, if you put I is equal to small I is equal to 1, then A of 100 is the reference of in terms of A. Similarly, you can check the B and C, and the transformation in general is fairly simple. So it preserves the original access order in the data space and generates the values accordingly. And this particular one also changes the index variable from capital I, which is going from 100 down to 20 minus 10 stride, to a simple one going from 1 to 9. So you can see that the iteration space of this loop now is simple, and of course you cannot change the data reference space because the data has to be in the right places. It's also to be generated in the same order as the original loop, and that is important, and that's what will be preserved here. So so now how do we really analyze, given this particular transformation, once we have the loop normalized in this particular way? The big reason for that is, let's assume in the previous example, two different loops, one followed by the other. And we'll come to such examples when we do the loop transformation. That is the main reason for doing it. When we have the transformation, the loop is going from lower bound to an upper bound, again with stride 1, the lower bound is always 1, and so on. So all these loops which are following each other will get normalized in this way. And then what we'll do is we will analyze if they have dependence between them. Let's say we have this particular loop as one loop. Maybe there is another loop over here which has similar going from one to something else. And then we'll analyze these loops in terms of whether they have any cross dependencies between them or not. And under certain situations, maybe we'll be able to fuse them together or merge them together. And that is where the loop normalization plays a key role. That because their lower bound is, all of them are normalized to 1, and their upper bounds will be whatever they are as per the original loop. We can take those two loops which share the same loop bound, lower loop bound, which share the same stride, which is equal to 1, and adjust their maybe upper bounds or whatever, and merge parts of them. And that will lead to an optimization. Why would it lead to an optimization? Because if we merge certain loops, the data which is there in these merged loops will have a better locality in many situations. For example, if A is accessed in a particular way in the first loop, and A is also accessed in the second loop, and if we put them in the same for example, then both A's will be found in the cache more likely, rather than the first loop completely executing, let's say, 1,000,000 times. And by the time that particular A will be evicted and will not be found in the second loop when it needs it. So by doing this loop merger, or what we call as fusion transformation, we are ensuring that data locality is mostly temporal locality is ensured, and that leads to a good saving in terms of the execution time and latency of the loop. So things like loop fusion, especially loop peeling, loop what you call it, the loop even fission. Sometimes you take a loop and cut it up into pieces because it may not have good locality, and the smaller pieces might have better locality. For all those reasons, you really need the normalization, especially for fusion and so on. So that's why you carry it out, and it also guides the analysis properly, because now you can see that the iteration space here in this loop is a consecutive or a convex space in the eye. It goes from one to the other without skipping any iterations. Whereas in the top level loop, it goes from 100 to 20. But if you ask, hey, is the iteration 92 a part of this space? It is not easy to answer it because this loop only goes on from 100 to 90 to 80. So 92 is not in the space. So if you generate some solution which is at 92 and that is not in the loop, then obviously you're generating something which it never executes. So whereas in this particular case, you can always say that it always executes all the iterations which are within the range, and you're able to reason on the range itself. So that's the reason for loop normalization. Now turning to these kinds of dependencies and how to analyze them, let's look at it, what really happens inside a loop. A very simple loop that we have. We have I going from 1 to n, and see what is going on here. You can easily see here that when I is equal to 1, we are generating a value here, which is a of 2, which is shown in the lower box. And in the next iteration, we are consuming it on the right-hand side, a of 2. And so there is a flow dependence, cross-iteration flow dependence. Many times the dependencies could be there, but they could be within a statement. For example, if this were also a of I is equal to a of I plus b of I, then a of I would be read first within a given iteration, and then will be added to b of I. and in the same iteration will be overwritten on the left hand side. So what kind of dependence is there? If both of these were A of I, that would be a anti-dependence, because it will be read followed by a write. But it's an anti-dependence which is within a iteration. And so if we're splitting this across different iterations, we won't have any dependence in that particular case, and will be still okay in terms of parallelization. In this case, however, that is not the case. This dependence is actually across iterations, because from first iteration we are going to second iteration and we are carrying a value here, and so cross iteration dependencies are problematic. In short, any kind of dependencies, they could be read followed by write, write followed by read, or write followed by write, and so on. So all these dependencies which are cross iteration dependencies will be problematic, and that's what our focus will be in terms of analyzing them. Intra iteration dependencies, even if they are there, they are not really relevant as far as we don't break down a particular iteration. If we break down the iteration, yes, they will be also relevant. Any questions thus far in terms of different concepts of dependencies, how we are looking at it, what we are trying to do with them, and because from here then we will get into different sort of definitions first, and then from we will try to get into different dependence tests. But let's see if we have any questions thus far in terms of what do the dependencies mean, how they are getting used, and so on. Okay, so then I think we'll just quickly introduce a couple of terms, and then we will get into what is called as a dependence. That will set the stage for dependence analysis. So what we typically do is we analyze a loop nest for dependencies, because obviously what we want to do is take that loop nest and then parallelize it. Like in this particular case, we did it. We took this loop nest, complete loop nest, which is a typically nested set of loops. We analyze these dependencies between, pairs of references to the same variable typically, because different variables, they don't need to be analyzed unless they're aliased. So we'll take this pairwise and we'll form dependencies, and we'll analyze if they are dependent or not. And that's why we'll focus on a given loop nest. And what we'll say is this loop nest, the iteration vector is, we'll designate that as ordered vector of I1, I2, I3, IN. Whereas this particular representation is telling us that it is a iteration number for loop which is at the nesting level, and the set of all possible vectors is the iteration space. So this vector is really showing you a particular element in the iteration space in an ordered way, where I1 is the outermost loop's iteration, I2 is the inner one, and IN is the innermost one. And so this vector shows you that, and the set of all such vectors shows you the iteration space. So here is a simple example of this iteration space. So we have a do loop, I going from 1 to 3. The inner loop is J loop, going from 1 to I, note that. And then we have a reference of A of ij is equal to A of j of I. So inner references are of course not relevant here. We are only talking about the way the loop executes. So the iteration space of this is the enumeration of all these vectors, which are these I and j traverse. So if we fix that I is equal to 1, the inner loop will traverse a space j equal to 1. So the first vector is 1, 1 here. Then the outer loop will go to I equal to 2, because obviously j can go from 1 to I itself, so it will not get past 1 here in this case. The j will go, so the I loop will go for reset back to the second iteration, so 2. Now the inner loop will span j equal to 1, so 2, 1 will be the next one, 2, 2 will be the next one. And then again, j cannot go past more than I, so it will reset I to 3. And so that the next iteration will be I equal to 3, j equal to 1, and then I equal to 3, j equal to 2, and finally the loop will end 3, 3. So this is the iteration space, which is a collection of all these vectors. And you can see that what is going on here is this space is getting traversed in a particular way, not in some arbitrary way. It traverses it from 1, 1 to 2, 1 to 2, 2 to 3, 1 to 3, 2 to 3, 3. So it is not that arbitrarily we start at 2, 2 and then suddenly go back from there to 1, 1. The reason is these I and j are nested in each other, and we start with the outermost loop, we keep it at its lower bound, then go to the inner loop and traverse it completely. Then we come back to the outer loop and so on. So there is an order of traversal that is associated with the iteration space in terms of one vector going to the second, to the third, and so on. Now that when we do that in the iteration space, what happens is at each iteration space point, we are also generating references using the underlying data spaces. And so what happens is when I is equal to 2, 1, the iteration space vector we are traversing 2, 1 here, the underlying execution traverses, if you focus on it, of A1, 2, which is j of I. So this particular R value is first traversed, and then it is assigned to 2, 1. So in short, the iteration space is traversed in a particular order. Each iteration space point or vector, we traverse the underlying data space from R value to the L value and generate these references. And then these references, in terms of read-writes, decide the read-write order of the loop's image on the data space. Now, if we preserve the same order by transforming the iteration space, we are just fine. However, if we violate it in terms of first something was being read, whereas now in the new order, first something else has been written, which was happening only afterwards. So if particular data space value was first being read, followed by being written in the original iteration space order, whereas in the transform iteration space order, we are doing it in reverse, that we are first writing into it and then reading into it. That's a violation, and that is what we do not accept because it will lead to long code. And that is what the problem is about, analyzing the iteration space and making sure that in that particular order there are no dependencies of these kinds. And if we do not have it, then we are free to reorganize it. If we have it, then we must respect them. We could still do some reorganization, but we must respect them. And that's the goal of dependence analysis. So first problem which we'll look at is just to find out if the dependence exists or not. And if it doesn't exist, then we have a lot of freedom and to transform it. And that's the next step that we'll be taking. So I will stop here, and from the next lecture, we'll be looking at how this lexicographic order that we found of iteration space traversal. What is the lexicographic order? Again, this is the order 1 1 followed by 2 1 followed by 2 2 and so on. How does this lead to the dependence problem, and how can we do some testing to check if the data space order that is imposed by this particular iteration space order is preserved or not. So we'll take a look next time, but we'll stop today. And if you have any questions, I'll be happy to see you in office hours. Thank you.